All right, in this portion of our presentation, we're going to actually go over exactly how do you split up your forces and look at diagonal forces and actually do some calculations. All right, so when we're adding forces, like in our previous examples, when we had a force up and a force to the right, and we wanted to find the total force, we're really going to add these forces using vector methods of adding. Now, there's different ways to add vectors, okay? So there's different methods we can use. There's the standard tip-to-tail method, right? And this is where you can, typically you draw your forces like this, right? Where the object is centered here, but you may not like that, right? When you're doing the tip-to-tail, because this is lined up tail-to-tail. So you can move, just like we showed before, the animation, you can move one of the forces so it is tip to tail, and then you draw a force from the very beginning to the very end, and that is your net force. Okay, and so if you can just literally just measure this or calculate the length of this line, you now know what the total force of these two added together is. Another trick to doing that, if you don't want to redraw your arrow in a new location, is you can do what's called the parallelogram method. And in this method, what you do is you basically turn your shape without moving an arrow. You turn it into a parallelogram. So it's like almost as if you drew this line up here, and it's almost as if you drew this line over here, right? And so if you did pick this up, right, and moved it over there, it'd extend, the net force would extend from here to this end. And so if you draw a parallelogram, the net force just goes from where the both are connected to where the new corner is. And that's a fast way to add them when you have a free body diagram. Now, actually calculating this is a bit of a pain when they're at angles. Luckily, most of the forces that we draw are at right angles. And when they're at right angles, like the ones we saw before in our previous example, how you add them becomes really, really easy because, right, we can, for example, I'll do the parallelogram method here real fast. If I want to find the length of this diagonal line, I say, hey, well, here's a triangle right here. The length of this line down here is the same as the length of this line up top, so I can imagine this force as being up here. And so really this is just a triangle and I want to find the hypotenuse. So I'm just going to use a squared plus b squared equals c squared, right? Where a is the force A and b is force B and c is the total force of them together. This is a way you can add your forces, and this is going to be the most common way, the Pythagorean theorem. It's going to be the most common just because we deal with a lot of forces that are at right angles to each other. But all these methods are equally valid. Now, more important than adding forces, we find ourselves usually splitting up the forces. So a problem where you might see something like this is like in this one, where you have a three-way tug of war, and instead of knowing what the force down and the force left is and trying to figure out the diagonal force, more commonly we're trying to do something like this, where we know the diagonal force, but we want to find the force down and the force over. And so we might say, well, this guy who's pulling diagonal, he's doing the job of someone pulling up and pulling to the right. That's what he's doing. He's pulling to the right and up. But in order to balance it vertically, I need to know what component upwards. In order to balance the equation, if this is, by the way, I forgot to state, is in translational equilibrium. In order to balance this and have no net force horizontally, I need to know that the horizontal component of this diagonal is equal to him. So this is not equal to 50. This is not equal to 50. It's this guy here is equal to the horizontal component of this 50 Newton force. So we want to, in other words, take this diagonal force and split it into two different forces, one going over, opposing this guy, and one component going upwards to oppose this guy. And just like before where we took two forces and represented it as one, now we're going to say, hey, look, we have one diagonal force, but I don't like diagonals. In fact, I hate diagonals. I want things to be always right across from each other. And it becomes a lot easier if you take something that's diagonal and represent it as two different forces in a way that's more convenient. So we're going to go through this process right now, and we're going to do it using trigonometry, and then I'll show you another trick. So let's divide it up. In order to do that, I'm going to draw the horizontal component of this force F. I'm going to call it F sub x, x meaning the x-axis on a graph or the horizontal direction. We often use x to mean horizontal. So this and you can see this diagonal force actually physically goes over this far and then stops, right? It doesn't go any farther. That's how I know how long to draw it. And we're going to draw the vertical component, and we're going to label it F sub y. So it's the force F, but the vertical component of that, y being the y-axis, vertical axis. All right, so I would like to calculate these two lengths of lines. I know this angle here. I know this length of the hypotenuse. I could try and use Pythagorean's theorem, but a squared, don't know. B squared, don't know. C squared, I know C, that's it. Two unknowns, that's not going to help. I'm going to need to use trig. So I have to review my trig functions. Sine is opposite over adjacent. Cosine is, sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. If you can't remember the trig functions, you can use the trick where people say SOHCAHTOA, S-O-H, for sine is equal to opposite over hypotenuse, etc. If you can't remember SOHCAHTOA, someone taught me, you can think, some old hippie caught another hippie tripping on acid. And that works for me. That's how I remember how to spell SOHCAHTOA, because it doesn't help if you can't spell SOHCAHTOA. All right, so let's use SOHCAHTOA. I want to find let's go find F sub y first, the vertical component of this guy. This is opposite of the angle, and I know the hypotenuse. So I want to use opposite and hypotenuse, that's sine. So I know the equation for sine is the opposite side, which in this case is F sub y, divided by the hypotenuse, in this case F. I'm going to solve for F sub y, so I'm going to rearrange, multiply both sides by F. I get this, and I can plug in some values, do my math, get an answer of about 30 newtons in the vertical direction. Let's do the same thing for the horizontal component, right? I want this is adjacent to it, so I'm going to, and I have the hypotenuse, so I'm going to use cosine. I rarely ever use tangent, so I'm going to use cosine. Cosine of the angle is the adjacent side, or F sub x, divided by the hypotenuse, or F, the full amount of force. And I'm going to multiply both sides, F cosine theta equals Fx, plug in my values, get about 40 newtons. So we can see, hey, look, this 50 Newton force here breaks down into a component vertically of 30 and a component horizontally of 40. And notice 40 and 30 don't add up to 50, but that's fine because this is a triangle. So now I say, okay, the whole original question was, what is F of A and what is F of B if it's in translational equilibrium? Translational equilibrium, again, means just that the net force is zero. Well, this free body diagram is useful, but sometimes it gets a little muddied when you have all these extra forces and this diagonal. So to be honest, this is what I call a free body diagram, like without these components here, these vertical and horizontal components. The free body diagram is the original blue diagram, but it's not a very useful one because it's got this diagonal. So I always like to create, after I draw my first free body diagram, what I call a working free body diagram. Here's what I would call a working free body diagram. I move the vertical component over here so that it looks nice, and then I usually I just erase this and get rid of the diagonal, because I'm basically replacing this diagonal with two separate individual forces, one up at 30, one over at 40. And now this problem becomes super, super easy. If the net force horizontally is 0 and this is 40, FA is 40. Vertically, if the net force is 0 and the force upwards is 30, this force downwards is also 30. Easy peasy. Now another way to solve a problem like this, it's the exact same problem as before, but another way to solve it with relative ease is to actually just use graph paper and a ruler. Let me show you how to do that, and you'll actually see it's less work. So if I wanted to do this, and I said, oh, I know I got a force at a 36.87 degree angle, and the force is 50 newtons, what I would do is I would use a ruler to draw on graph paper, and I'd pick a scale. For example, maybe I might say, okay, 5 centimeters here is going to equal 50 newtons. Or in other words, my scale is 1 centimeter is equal to 10 newtons. And I've got to actually physically draw an arrow at the right angle, 38 point whatever degrees, or thereabouts. 36 is, I believe, what it was. And I've got to draw that right length. And if I do that, this is actually really easy. Watch. And that's like the hardest part, is just drawing the line. Once I've got that drawn to the right length, I say, oh, okay, so how much up does it pull? Well, if this was 5 centimeters long, I can literally physically just measure these two values right here. Let me draw the same triangle, the same forces in, right? I've got a force over, force up, and now I just need to measure it. So I measure this force over, and this is, well, 4 centimeters long. 1 centimeter is 10 newtons, boom, 40 newtons. That's the answer. What is the vertical component of that? Well, it's 3 centimeters long, right? Hey, 1 centimeter is equal to 10 newtons, so 3 centimeters is equal to 30 newtons upwards. Man, that was easy. And now I can do the same thing, make a working free body diagram and say, well, if up is 30, down is 30. If to the right is 40, to the left is also 40, assuming I'm in translational equilibrium or no net force. Now, both methods are equally valid and both methods work. You can use trig, you can use a graph paper and a ruler. And on the test, you can actually ask for a graph paper and a ruler, and you can actually solve that way. So I encourage you to even try it out a couple of times and see which way you like best. Unfortunately, every now and then, though, we ask a question where you actually have to split up the arrows and you have no numbers. So for example, this is the same kind of problem, but instead of saying the force is and giving a number, we're actually just saying the force is F. I don't actually know what the force is yet. Maybe the problem's going to have you solve for that force. You don't know what it is. So it's an unknown amount, a force of F. And then the angle, I don't know the angle either. It's an angle of theta, okay? And that's just a general angle. I don't know what it is. Maybe I have to solve for it. I don't know. But you still, in a problem, can't solve until you split up that force. So how do you do it? Well, you do exactly what you just did, but you have to use the trig. Doing the arrows with on the graph paper doesn't work so well. So let's see what that looks like. And you're going to see it looks very similar to what we just did. I'm still going to draw the horizontal component. I'm still going to draw the vertical component. I'm going to solve for the vertical component using the same equation, right? Sine of theta is equal to the opposite over hypotenuse. I'm going to rearrange and just solve for f sub y, okay? Now, I've just solved for f sub y. Now, this is as far as I can go. I can't plug in an f value because I don't know what it is. I can't plug in a theta value because I don't know what it is. So this is your vertical component of the force. We say that this value right here is equal to f sine theta. That's what it is. And in fact, a lot of the times, we won't even label it f sub y. We'll just say f sine theta, because that's the amount of force that it's going to be relative to f and theta. Let's do the other one. If this was f sine theta, can you guess what this one's going to be? Well, last time we used cosine, right? So we're going to use cosine again. Adjacent over hypotenuse. We're going to rearrange, multiply f by both sides, and I get f cosine theta is my horizontal force. And this is my answer, right? And I'm just going to leave it like that. Now, I know that's not very satisfying because you have no number, but leaving it in this form will, in some way, eventually help you to actually solve for your force that's diagonal in a problem when you don't know it. But you've got to go through this process. Now, here's the cool thing. It's always these two equations. If your force is F, then one of them is going to be F sine theta. One of them is going to be F cosine theta. And that's always what they are. One of them, and you know, if the force is a tension, then it'll just say T sine theta, or F sub T sine theta, or F sub T cosine theta. And that's it. It'll always be in the shape of one of those two. And then you really just have to decide, wait, which one's F sine theta, which one's F cosine theta? And you just have to go through that process. Well, sine is always opposite, right? So the one with sine will be always opposite of the angle, and the one with cosine will always be the one adjacent to the angle. Now, in class, you'll practice a lot more of these problems. Good luck.